Hi, welcome to this video on the reactivity series. So what you can expect from this video is that we can rank metals in terms of their reactivity using their reaction with water and acid, and we will discuss that in more detail. We'll discuss the fundamental reaction that takes place when a metal reacts. So for example, in this case, calcium is reacting to give its calcium positive ion plus 2 electrons. And we'll also use the reactivity series to predict and explain displacement by metals. So if we have a salt, for example here copper sulfate, and we react it with magnesium, then magnesium can replace copper, giving us essentially pure copper and a magnesium sulfate salt. And we'll also explain that in terms of the reactivity series or their relative position in the reactivity series. So the reactivity series, so here we have a list of elements: potassium, sodium, lithium, calcium, magnesium. For reference, people like to include carbon, zinc, iron, and then we have the sort of least reactive. We have hydrogen and copper at the bottom, and the carbon and hydrogen are just for reference, so that chemists can kind of say relative to carbon or relative to hydrogen. Now metals can react with water. They can also react with acids. So above that first yellow line, you can see calcium, lithium, sodium, potassium tend to be able to react with water. Below that yellow line, magnesium, zinc, and iron tend to be able to react with acid, and then copper is the least reactive. Now, when these metals do react, for example, potassium, when it reacts with water, or sodium, lithium, and calcium, when they react, they're essentially giving up an electron and forming the positive ion, and there's an electron released. When sodium reacts, it forms its positive ion, and an electron is released. And it's the same for lithium. When it reacts, it forms its ion and an electron is released. Now calcium, because actually it has 2 electrons, then actually when it reacts, it forms a positive ion as well, but actually releases 2 electrons. So that's fundamentally what happens when metals are reacting. Now these three at the sort of top of this series are the group 1 metals: potassium, sodium, and lithium. And they are reactive enough to react with water, whereas calcium and magnesium are really group 2 metals, and their reactivity is a little less, and they tend to react with acids. And then the least reactive here are these transition metals: zinc, iron, and copper. And they then they will tend to react with acid, but the copper itself is actually quite inert or unreactive. So if we take the metal and we react it with water, then we can get a salt, and we can get the release of hydrogen gas. And if we think in particular of potassium will react with water to give us potassium hydroxide plus hydrogen gas. Similarly, now that's it's quite a reactive reaction, so you can get a flame, and with potassium in particular, you can actually get an explosion. That reactivity decreases when we go for sodium, but it's still quite a vigorous reaction. So sodium reacts with water to give sodium hydroxide plus hydrogen gas. Lithium reacts with water to give lithium hydroxide plus a hydrogen gas. Now with those metals that are less reactive, then we need something slightly stronger. So there we have an acid. So magnesium will react with acid. Metal plus an acid will actually again give you a salt plus hydrogen gas. Zinc and iron will also react with acid, whereas copper is the least reactive of these in this particular series and does not react with dilute acid. Now, as I said earlier on, the potassium, sodium, lithium examples are reactive and react with water. The magnesium, zinc, and iron tend to react with acid, and then that copper I said didn't necessarily react with dilute acid. So copper's at the bottom of this reactivity series and could be described as the least reactive, whereas potassium is at the top of this reactivity series and can be described as the most reactive. Now there's a sort of usefulness to this, because in fact we can use the reactivity series to predict and explain displacement reactions. So let me give you an example. I've got copper sulfate, and if we add magnesium metal to a solution of copper sulfate, then in fact, because copper is essentially at the bottom of our reactivity series and magnesium is higher up, magnesium is more reactive than copper, and it will actually end up displacing the copper ion, and we'll have magnesium sulfate, and copper ions actually become copper metal. So copper sulfate plus magnesium metal gives us magnesium sulfate plus, I want to say pure copper, but copper metal. Now, if we think about iron sulfate, for example, and we try to react that with copper, now iron is above copper. So can you predict whether those will react or not? I'll give you 3 seconds. So the answer is they don't react, and that's because iron, which is the more reactive, is already reacted. It's already with iron sulfate, and so copper can't actually displace iron from iron sulfate. So that reaction does not actually proceed. So we can use the reactivity series to predict whether one metal can displace another metal from its salt. And in that particular case, magnesium will displace copper, but copper will not displace iron. So in summary, when a metal reacts, it loses an electron to form a positive ion. The ability to lose that electron is sort of predicted by the reactivity series, with potassium being the most reactive and the most likely to form a positive ion and give up an electron, with the copper least reactive, with the least ability to form a positive ion and give up electrons. And then we can use the reactivity series to predict whether one metal can displace another metal from its salt. So we'd use the example of copper sulfate. Magnesium is higher in the reactivity series, and so it can displace copper from its salt, and we'll get pure copper in that particular case. If you do have any questions, don't hesitate to reach out to us. Okay, thanks very much.